Okay, so let's think about what Taylor and Maclaurin series are. The main question that we're trying to answer is that if we have a differentiable function on an interval, can we write it as a power series? When we worked with power series, we were given what the series looked like and we thought about where does the series converge for what values of x. But now our goal will be, if I just know what a specific function, can I write it as a power series? Because if I can, we may be able to do operations on it that are too difficult to do on the function itself. So the way we're going to start that is, let's suppose that we have some generalized function here on some interval. We're going to call it f of x. And the first thing that I'm going to do is start to generate a polynomial that matches the function at 0. So I'm interested in matching the function as closely as I can at when x equals 0. We're going to call that the center of our series. So the first thing that we're going to do is the easiest thing I can do is I define a new polynomial so that it matches the function at 0. Well, that's a really bad match, right? Because that's just a straight line. Here's f of 0. So the first polynomial that we're matching is just a straight line that looks like this. It's not a great match around the area of 0 to our function, so it's not great, but hey, it matches the function at least at one point. And the question becomes, how can we make this better? So we're going to then create another polynomial. So I'm going to just label this 1 for our first approximation, not so good. Our second one, well, I don't just want to match that point, but now I would also like to match first derivatives. So I'm creating a new function, a polynomial, so that the derivative at 0 of that polynomial is the same as the derivative of our function at 0. Why is that a good thing? Well, we know that the tangent line at a point is the best approximation to the curve at that point. So that's what we're going to do. We're going to write the tangent line at this point. So the tangent line is going to be at 0. Well, our tangent line will be the y-intercept, which we know is f of 0, plus the slope, which we know is the derivative at 0 times x, right? This is our mx plus b. Here's mx plus the y-intercept, and this is the equation of the tangent line. So what does that gain us? Well, we do gain something here, because at 0, if I draw the tangent line, well, it's not a perfect approximation to the curve, but it's better than what we had before. Is it true that the derivative of our tangent line, so here's our second polynomial, let's test to see that its derivative at 0 does in fact equal the derivative of the function at 0. That will mean that they match derivatives. That's a good thing. So let's take the derivative, p prime of x. Remember, f of 0 is a constant, so its derivative is 0, and the derivative of f prime of 0x is just f prime of 0. So if I evaluate this at 0, yes, we have this is equal to f prime of 0, and the derivatives match. So we have two polynomials. The first one's a straight line, not so good, the red one. The second one's the blue one, that's the tangent line, that's better. Let's see if we can do better and match concavity. That means we're going to try to match second derivatives. Okay, so we're going to create a new polynomial, p of x, and what I want now is to match concavity. I would like the second derivative at 0 to be the same as the second derivative of our function at 0. So here's how we're going to do it. We're going to create p of x. I'm going to just add to what we already had in blue over here. I'm just going to add to that. And we'll start with f of 0, then f prime of 0x. There's our tangent line. And now I'm going to add a third term, the second derivative at 0, x squared. And I'm going to divide this by 2, and you'll see why. So we have a little bit of work to do to figure out, will this new function, let me label another little blue dot, this is our new one, will this one give us match second derivatives? That's what I want to see if it will do that. So let's see. I'm going to take the first derivative of the new polynomial that we have here. We know the derivative of f of 0 is 0. The derivative of f prime of 0x is just f prime of 0. And here the derivative, and this is why you can see I'm dividing by 2, will be f double prime of 0 over 2 times 2x. And that's nice because my 2's will cancel out. So right now we have that the first derivative is f prime of 0 plus the second derivative at 0 times x. But remember, we wanted to match second derivatives. So will the second derivatives match? Well, the derivative of this, that's just a constant, so it's 0. And this will be f prime of 0. And sure enough, at 0, these second derivatives are a match. What does that mean graphically? Well, graphically it means that what we've been able to do is a new function that now matches slope but also matches concavity. So that green one would be our new polynomial that I wrote over here. That's the new one that we matched. So that's the idea. The next step would be let's match third derivatives and then fourth derivatives and so on. But instead of going on and on and on and repeating the same process, so here's the idea. We are creating a polynomial function. We are creating a polynomial whose derivatives, all of them, if we can, will match the derivatives of our original function. Match. And that means that we're fitting better and better, closer and closer to the original function at the point where we're evaluating this. Remember, the center here was 0 because I was only really paying attention at x equals 0. And so what this would look like would be f of 0 plus f prime of 0x plus the second derivative at 0, x squared over, actually it's 2 factorial, but 2 factorial is 2, plus the third derivative at 0, x cubed over 3 factorial, and we keep going. And if I make this an infinite series, that's called, so I'm going to write the nth derivative at 0, x to the n over n factorial. And if we keep going and make this infinite, we have just developed something called the Maclaurin series for our function f. That's what we have just developed. What was the idea? We wanted to come up with polynomials and then eventually an infinite polynomial, that means an infinite series, whose derivatives match our original function so that graphically, at the center at least, we're getting better and better matches to our function. I'm going to continue this in our second video.